Good morning, grade 10s. Welcome to a third lesson of measurement where we're doing surface area and volume. In your first lesson, you saw the 3D shapes that you were very familiar with: triangular prism, rectangular prism, and cylinder. In our second lesson, we did conversions, and today in our third lesson we're doing shapes that you have not yet seen before. And the first shape we're doing today is a sphere, and that's what you have in front of you. And a sphere is a perfectly symmetrical ball with all points on the surface of the sphere being equidistant from the center. So that means if I took any point on the outside of my sphere and I took it from here and I ran it inwards to the middle of my sphere into the center, all those points would be equidistant. Why? Because they're all like radii. Each one is a radius. These are the formulas on surface area and a volume shown before. So the surface area of a sphere is 4 times pi r squared. What do we recognize pi r squared as? Pi r squared is the area of a circle. So we've got 4 times the area of a circle. The volume of a sphere is 4/3 pi r cubed. We haven't seen pi r cubed before, but why do you think it's cubed? Because we're doing volume. And remember, volume, we always need to multiply 3 things together. And when we did a cylinder, we multiplied pi r squared with the height. Now we're doing a sphere, and we're basically multiplying pi r squared with another radius to get the 3D shape of a circle. And it's 4/3. So this is a sphere. And then the other thing we have, if we cut the sphere in half, is something we call a hemisphere. So now, I'm just going to stick a lid on this. This is going to be called a closed hemisphere. And you saw I had this on the top and I took off half of my sphere. And now we have in front of us a hemisphere. So, a hemisphere, a volume, whether it's open or closed, it doesn't matter, the volume remains the same, is a half of the volume of a sphere. This was the volume of our sphere, and a hemisphere is half of that because you saw I took half away, so that's easy enough. And when I simplify the half times 4/3, I get 2/3 pi r cubed. That's a hemisphere whether it's open or closed. Now I should have written closed first because that's what I'm going to talk about. So the closed hemisphere is when I've got this lid on top of my hemisphere. And what do? We half the area of a sphere. Okay, and when I simplify half the area of the sphere, I must also add the area of the circle on top. So because it's closed, I've also got the circle that's on top. And that's why I half the surface area of a sphere and I add the area of a circle because we've got this circle as well. So we've got half the surface area of a sphere plus the added circle. When I simplify this half times a 4, I get 2 pi r squared plus the second pi r squared, which was the circle. And these two are like terms. I've got 2 pi r squared plus pi r squared, which leaves me with 3 pi r squared. So the surface area of a closed hemisphere is 3 pi r squared. If I just had to take this lid off and I have an open hemisphere now, the surface area is simply half the surface area of the original sphere, because here's my original sphere and I have half that surface area. And when I simplify that, I just get 2 pi r squared. There is no lid, so I don't add on an extra circle like I did with the closed hemisphere. So those are our 2 shapes that we've just seen now. A sphere, which is a completely cylindrical, symmetrical ball, and then we've also got on the other hand our hemisphere, which can be closed with a lid or it can be open with no lid inside. The second shape that we're doing today is a pyramid, and these are 3 different types of pyramids in front of us. What is the difference I want to show you between a pyramid versus the shape we've seen before, which is a rectangular prism? So let me just compare these two so that I can show you. This was a rectangular prism. And what did we say a rectangular prism was? A rectangular prism, or a prism rather, is a shape that has identical ends. So there's a I'm talking about a triangular prism, not a rectangular prism. A prism is something that has identical ends. So there's a triangle and there's a triangle on the other end, which are parallel to one another. So you can agree that that line running there is parallel to that line, and that line there is parallel to that line. And that makes a prism, particularly a triangular prism. So what would be the difference between this triangular prism versus this shape in front of you that I call a pyramid? And I'll tell you what it is. A pyramid has this point at the top called an apex, where all the points meet. It's not a prism because I don't have the same sides. Like this one had the same triangle here and the same triangle here that were parallel to one another. That's not the case in this pyramid. This pyramid has an apex. It's got a base. And from the base, all the vertices, all the edges, meet at a point that is directly above the center of there. So if you can see this point and there's a circle in the middle, they are directly above one another. So it's perpendicular. So that's the difference between a triangular prism versus a pyramid. So here's our 3 pyramids that I'm going to look at. And particularly I'm going to talk about a pyramid with a triangular face. So there's a triangle at the bottom, but all the points meet at the apex at the top. So I've got a triangular pyramid, or a triangular based pyramid. This pyramid over here, the base is a square, could be a rectangle, just that it's a quadrilateral. It has 4 sides, okay, a square or a rectangle, that then meets at an apex at the top here. And then I'm also going to show you this pentagon-faced pyramid. Why is it a pentagon? Because there's 5 sides, and from those 5 sides, they all meet at the apex over here. I'm just going to keep one in front of you, or I'm going to show it with each of you. Let's look. The volume and the surface area don't change for any of these. They all stay the same. So the volume of a pyramid is the area of the base. What do I mean by the area of the base? It's this shape. So if I had a square, for example, the area of the base would be side times side. If I had a rectangle, if this was a rectangle shape, the area of the base would be length times breadth. If I had a triangular based pyramid, the area of the base would be half base of this triangle times perpendicular height of this triangle. And if I had an octagon face shape, it would be the area of an pentagon, the area of this pentagon. And I'm going to show you just now how we find areas of these shapes that we are unfamiliar with. So for example, with this pentagon. And what do I multiply it by? I take the area of the base and I multiply it by the perpendicular height. What do I mean by the perpendicular height? It's that height that runs from the apex to the center. So that height running from the top point to the center of the circle of the base over here. So it would work the same, that perpendicular height from the apex here down through the center to that bottom circle there at the bottom. So that's height. And the same with this pyramid, from the top here down through the center there would give you the perpendicular height. And I take that and I divide it by 3. And just now I'm going to show you why we divide it by 3. We're going to conduct a very exciting experiment, but we divide the volume by 3. Right. The surface area of any one of these three, even if you had an octagon-faced pyramid, okay, is the area of the base plus the area of the triangular faces. So, the area of my base is easy. This would be a square area, so side times side, or if it was a rectangle, length times breadth. The area of this base would be half base of this triangle times the perpendicular height of this triangle. And then again, we'd have the area of the pentagon, which I'm going to show you how to work out, plus the area of the triangular faces. Because you can agree, no matter what base we have, each of the faces coming up to the apex are all triangular faces. There's a triangular face with a triangular base. These are all triangular faces, even though it's got a square base. These are all triangular faces, even though it's got a pentagon base. Okay, now this is the important part. How do we find the area of these triangular faces? And that's what this third formula is. The area of the triangular faces, so these faces, not the base, the faces that come up to the apex, are half base, like we would an original triangle, times the slant height. What is the slant height? If I had to draw the slant height up here in Koki, I hope it comes out, it would be the perpendicular height on the slant. So this would be my slant height. If you can see it from the side, it is not this perpendicular height that runs from the apex to the center of the base, but rather it is the perpendicular height running on the triangle, and I call that my slant height. If I had to do my slant height on this triangle, for example, it would be the height, the perpendicular height of this flat triangle. There's my slant height. Again, it's not this height that runs from the apex to the base, but it's the height on the side, the slant height. And this slant height would look something like this. There's perpendicular, right? And there it is again. It's the slant height. It runs up at a slant. So I'll just repeat myself. The surface area is the area of the base plus the area of the triangular faces. And it's not difficult to remember the area of the triangular faces. It's the normal, half base times height. But what height? The slant height. Because remember, this perpendicular height up here when we do volume is the height from the apex to the center on that side. And that's our pyramid. And the third shape we're doing today is called a cone. Now, a cone is also a type of pyramid. Why? Because I've got I've got an apex, but my base is circular. So it creates this circular shape coming up to the apex, okay? And if I had to draw this as a net diagram, when I had my normal pyramid, we spoke about the triangular faces that would make up our net diagram, because I'd fold the triangle down there, I'd fold that triangle down there, and I would fold the third triangle down there. But with a cone, I don't have triangles to fold down. So when I draw a net diagram of a cone, it looks something like this, okay? Right? And that is called a sector. So if I had the net diagram, I would have the sector. Plus, if it was a closed cone, I would also have then the circle making up my net diagram of this cone. When we're dealing with a cone, you're often having to deal with Pythagoras, because we've got a right angle triangle, because from the apex to the center of the base, if I had to do it this way around, we've got a perpendicular line that hits at 90 degrees in the center there, okay? So that's our perpendicular height, our little h. We've got a radius running from the center of the circle to the side of the cone. And then again, just like we had in our in our pyramids, we've got a height slant. So we've got the perpendicular height that runs from the apex to the center, but we've also got a height slant. And if I had to draw it very quickly on this cone, the height slant would run like that. And can you see that if I had to take this off here, if I can, and yes I could, I took it off, there's my height slant, and there's my radius running, and there it makes, I wonder if you can see it, a right angle triangle. If I had to think of sticking a stick through the middle there, okay, obviously this is too big, but there would be a line running downwards, there would be my height slant, and there inside, you can see I've drawn, is my radius. So we have to know Pythagoras, but we do know Pythagoras well. So this is the experiment we're going to conduct. Whoopsie, sorry. Right, we're looking at the volume of a cone. So the volume of a cone is 1/3 of pi r squared times height. What do we know is pi r squared times height? Well, from the lesson we learned, our first lesson, pi r squared times height is a cylinder. Here's my cylinder. Okay, so you can remember a cone because it's pi r squared times height. But my question is, why on earth would it be 1/3? That means that because they have the same base, you see how this has a circular base and this has the same circular base, they've got the same radius and the same diameter, right? That means that 3 of these cones, 3 of them, because a cone is 1/3 of a cylinder, can fit in here. And I didn't believe that until I conducted this experiment. So I'm going to show you how 3 of these can fit into here using water. That means I'm going to be able to fill this up 3 times, and this then I'll get a full cylinder. And remember that not only do they have the same base, the same shape base, they also have the same perpendicular height. Remember a cone was pi r squared times perpendicular height? Sorry, a cylinder was pi r squared times perpendicular height. That means they must have the same perpendicular in order for this to be 3 times bigger or for this to be 3 times smaller. They must have the same perpendicular height and they must have the same radius, which means they must have the same base. So that's what I'm doing. I'm going to fill this cylinder up with 3 of these cones. They have the same perpendicular height and they have the same size base, circular base. So I've got my cone here and my cylinder over here, and we're going to fill this to show you that 3 of these fit into 1 cylinder. So in goes my water. Looks like Coke, not Coke. It's actually like iced coffee. So I fill my cone. Obviously I'm not filling it right up to the brim because I'm going to spill, and very gently I'm going to pour it into my cylinder. I hope you can see that if this is the height of my cylinder, that it's not completely in eye level, is 1/3 of the cylinder. Still don't believe me? Let's add another one. Again, we're trying to get it as full as possible, but I may spill, so not filling it right up to the brim. There's 2/3 into my cylinder, and I'm going to put 1 more cone in there. And there's my full cylinder. What is this missing bit? It was just because I didn't fill this right up to the brim because I was scared of spilling. But if I had, I promise you, my entire cylinder would have been filled. So what does that mean? That means a cone's volume is the 1/3 of a cylinder's volume. And that's how we get this formula, 1/3 of a cylinder. Pi r squared times perpendicular height. Remember, perpendicular height, if we were looking at the cylinder, would be the height from this top to that bottom, meeting at 90 degrees, or the perpendicular height looking at this cone would be from the apex through to the center at the bottom. That's that perpendicular height. So, whoopsie, here's my cone. Now we've looked at volume. Now we're going to look at the surface area of a cone. And it's a closed cone, so I do need to get this lid on it, but it fell off. So, closed cone. Okay, right. This formula for a closed cone is half the circumference times the height slant. Remember, the height slant is that one running down there, plus the base area, or the area of the base. So how does that work? This formula here, half times the circumference times the height slant, gives me that sector shape that I showed you right in the beginning. That gives me the area of this shape, because this would be my height slant. There's my circumference, right? And so half times the circumference times the height slant. This is not drawn to scale, by the way. I just wanted to show you what it would look like in a net diagram. So that's my sector, plus the area of the base. What is that area of the base we're adding on for surface area? It's the space, circle. So we've got half of 2 pi r times the height slant, plus pi r squared. Where does that pi r squared come from? It comes from the circle that closes this cone. So simplifying that formula, I get pi r times the height slant plus the area of the base, pi r squared. If it was open, very similar. We just remove the circular base out of the equation. Literally, we remove the circular base out of the equation. There's my equation at the end. It's half the circumference times the height slant to get this net diagram, the sector, and we don't add on a base because it is open. So all this is a sector. And we get pi times radius times height slant. And those are the 3 shapes we're going to deal with now in our examples. So your first example has a little paragraph on the top of it that says, the Louvre pyramid, located in Paris, is a large, right, square pyramid made of metal glass. It serves as the main entrance to the Louvre Museum, which houses famous paintings of the Mona Lisa. The length of one side of the base is 35,4 meters, and the height is 21,6 meters. The base of the pyramid is open. And we're asked to calculate the exterior surface area, or the metal and glass of this pyramid. And everything is given to you that you need in this picture. It's square, told us it has a square base. So that's why we've got 35,4 over here, 35,4. The 21,6 is the perpendicular height, and they've given us then the halfway from the center to the outside of the type of radius, if you would. But half the length of 35,4 is 17,7. And we're asked to calculate the exterior surface area, and it doesn't include the base. So that means the surface area is just 1, 2, 3, 4 triangles that we are calculating. And I wonder if you can agree with me that actually all 4 of these triangles are exactly the same, because they have the same length at the bottom. They're going to have the same perpendicular height over here on the height slant. So the surface area is just going to equal the 4 times the triangular faces. I'm saying 4 times the triangular faces because all 4 of these are exactly the same. If it was a rectangle, that wouldn't be the case. If it was an octagon, if it was a pentagon, those kind of things may be the same, but this 4 comes because this is a square. So all 4 of these are triangles. Triangular faces are exactly the same. And how do we calculate the triangular faces? It's half times the base times the height slant. Remember, the height slant would then be this, which we do not have, but luckily we've got a right angle triangle, and that means we can use Pythagoras. So Pythagoras says, and you must show this for your marks, that the height slant squared should equal to 17,7 meters squared plus 21,6 meters squared. And you can put that straight into your calculator. And you get 779,85. And the last step is to square root that answer. I'm looking for my other square root. And you get 27 to 2 decimal places, 93 meters. Remember, it's a length. It's the length of this, so it's just meters. So if I had to substitute in here, we've got 4 times half times the base of the triangular face. So here's the base of the triangular face, because here's where they meet at 90 degrees. So we've got 4 times a half times 35,4 times then the height slant, which was what we got here, 27,93. And again, you're going to put that into your calculator. If you wanted to, you could see that 4 times a half, these cancel and immediately give you 2 right off the bat, because 4 times a half is 2. So 2 times this, put it into your calculator and get an answer. And your answer is 1977,44 meters squared. Remember? Because it's surface area. So it's 2-dimensional shapes, so it's meters squared. So that's the answer to A. So the second question asks us to calculate the volume of the pyramid. And we discussed earlier that the volume of the pyramid is the area of the base times the perpendicular height divided by 3. Why would we divide it by 3? Remember, instead of saying divided by 3, we could say 1/3 times the area of the base times perpendicular height. It doesn't matter which one you do. Where does this third come from? If you think about that experiment we carried out with the cone and the cylinder, the exact same thing would happen with a square-based pyramid, because it meets at an apex, and a cube. As long as they have the same perpendicular height and they have the same base, I don't want to tip this in case the sand falls out, right? Then 3 of these would fit into one of these, just like we did with the cylinder and the pyramid and the cone. 3 pyramids would fit into one of these cubes. So that's why we get that dividing by 3 or 1/3. So area of base, it is a square. So I know the area of a square is side times side. So, or side squared. The side is 35,4. So we've got 1/3 times 35,4 squared, that's the area of my base, times the perpendicular height. The perpendicular height, remember, runs from your apex down to the center of your 3D shape, and that was 21,6. And you put that into calculator and you're going to get an answer. And you end up with 9022,75 meters cubed, because it's volume. So we have meters cubed. And that's how you work with a pyramid. Remembering the difference between a pyramid and a triangular prism, a pyramid has this apex over here. Question example 2 reads, calculate the volume of the equilateral base pyramid shown below. If the pyramid has a height of 18 meters, and that's the perpendicular height running from the apex to the center, can you see that perpendicular sign over there, right? And the length of the base is 4 meters. Okay, cool. So we've got this equilateral triangle base, which I'm just going to draw over here, the 2D shaped base, which is equilateral, and they're all 4 meters in length. Okay, now remember, the volume, because we're asked to calculate the volume, is equal to a third, or you can divide by 3, a third of the area of the base, this being my base, right, times my perpendicular height, being this line here of 18 meters. Okay, how do we find the area of this base? Remember, the area of a base of a triangle is half base times perpendicular height of the base. So, the base is definitely going to be 4. If I took, for example, my perpendicular height, this is not drawn to scale, my perpendicular height would cut this into 2 equal triangles if it was drawn to scale. I'd have a triangle on this side that was identical to the triangle on this side. I do not have my height. I only know that this is equilateral. So what I'm going to do is I'm going to use Pythagoras. I'm going to use one of these triangles over there. So I'm going to take that triangle out. I know this is 4. I know this is 2 because the perpendicular height would cut that length in half. And I'm going to figure out what the perpendicular height is of this triangle. Not what the perpendicular height is of the pyramid, but of the triangle. And I'm going to do that using Pythagoras. So you must please show this to work to get all your marks. So I'm going to just show here that the perpendicular height of the base, right, is going to be like this. The perpendicular height squared should equal 4 squared minus 2 squared, because I've got my hypotenuse, so I must be subtracting. 4 squared is 16, 16 minus 4 is 12, and the last step is to square root, and I'm going to leave it in surd form, which I should actually do always. I'm going to leave it in surd form because that's not a perfect square instead of rounding off. So we have the exact measurements. So I'm going to now erase this, but do you agree that the perpendicular height of the triangle that I'm going to use here in this formula is going to be the square root of 12? I don't have enough space, that's why I'm erasing this, so please make sure you've written it down. And now I substitute in. Volume equals a third times my triangle. Half times the base. The base is this full line here. 4 times the perpendicular height, which is that line there, which we said is the square root of 12. Multiplied by the height, the perpendicular height of the pyramid, which we know is 18. And we're going to fill that into our calculator, and we're going to get an answer. And you end up with 41,57 meters cubed. Meters cubed because it's volume. So because we've been dealing with pyramids, I just want to talk to you about other based pyramids. So it would be easy if it's a square base pyramid to find the area of the base. We know it's side squared. It's easy if we have a rectangular base pyramid because we know it's length times breadth. It's easy even if we have a triangular base pyramid, which we know is half base times perpendicular height of the triangle. But what happens if we have a different shape based pyramid? So for example, a pentagon, which is a 5-sided shape, looking like this. How do we find the areas of different shapes? And how we do that is from one vertice to another, we see how many triangles we can draw without crossing lines. So for example, I'm going to go from this vertice and I'm going to draw a cross. There's one triangle. And from this vertice, for example, I'm going to draw a cross over there, and there's two other triangles. I couldn't draw from another vertice without crossing over. So this is made up of 3 triangles. So the area of this shape would be 3 times half base times perpendicular height of these triangles. There's 3 triangles in here. Okay, so you'd work out the area of that triangle, you'd work out the area of that triangle, and you'd work out the area of this triangle. Okay, they're not all the same, so it actually can't go 3 times the same formula, because not all of these triangles are the same, but there are 3 triangles in there. So you'd work out the area of the 3 triangles, for example. And that would happen with any shape. I'm going to try my best to do a 6-sided shape. There's a 6-sided shape. And how many triangles can I fit into a 6-sided shape? 1, 2, 3, 4. So I'd work out the area of 4 triangles, basically. And that's how you would do the areas of different bases if you had a pyramid of a different base. Interesting enough, that's also how you figure out the interior angle size of a triangle of a different shape. The interior angles, so in other words, all the angles on the inside of the shape, okay, would equal 3 times 180. Because I've got 3 triangles, and I know that each triangle, it comes to 180 on the interior here. So this shape, 1, 2, 3, 4, I can make 4 triangles, so it'd be 4 times 180. If I ever wanted to know how many degrees the shape was made up of. That's just a side note. And our third example today says an ice cream cone display is constructed from a solid cone and a hollow hemisphere shown below. Calculate the surface area of the display. Hint, the ice cream has to fit exactly on the cone. So in other words, the ice cream circumvents the cone. It fits exactly onto this circumference, is exactly the same size as this circumference. Because this must fit onto the cone exactly. So if I had to use my 3D shapes, this would be it. You could do it differently. You can work it out individually, my hemisphere, and you can work your cone out and then add it together. But what must you do? You must make sure you're working out an open hemisphere, and you must make sure you're working out an open cone. And that's actually how I'm going to do this. An open cone. Can you just pretend that, I don't know why I struggle to take this cone's lid off. Let's just pretend that the lid comes off. It must be an open cone. I must be able to put my hand in. Okay, if you're working them out individually, which I'm going to do, it's an open hemisphere and an open cone. And that's what we're going to do now. So, you would agree with me that they would have the same radius. So this radius is 6, this is going to be a radius of 6. I know that this makes a right angled triangle, and I know for my formula, I need this over here, which is my height slant. So that's what I'm first going to figure out using Pythagoras. So my height slant squared must equal 8 squared plus 6 squared, which gives me 100. And I must always square root it, so I've got 10. So this is 10. I wonder if this is in centimeters. It's quite a big ice cream cone. So the height slant is 10. I'm going to erase this now because I need the space. And under my cone, it's an open cone, I know that my surface area on my cone is equal to half the circumference times the height slant. If it was a closed cone, I would add on the area of the circle, but it's an open cone, so I don't add on the area of the circle. The circumference is 2 pi r, so I've got a half times 2 pi r times the height slant, and what do I know with this half and the 2? They cancel out one another. So all I'm going to fill in is pi r times height slant. This is not a necessary step to follow. I just put it in my brain because this is what I remember. And then I fill in what I remember and I get to my conclusion. But if you can remember this straight off the bat, you don't even have to fill that in there for me. You could just say that the surface area equals pi r times the height slant. So I'm going to fill in what I know. It's pi times r, my radius, which is it 6 or is it 9? I'm making it 6, okay? Or what did I use? Yes, I'm making it 6. So, you can't see if it's 9 or 6. I'm sorry if someone disagrees with me. I'm using 6, okay? I'm sure it's 6. Why? Because it came out very nice in this Pythagorean triplet with 8 and 6, and I got 10 over there. So I'm keeping it 6. So pi times the radius, which is 6, times the height slant, which is 10. That is 60 pi. I'm going to keep it like that, and I'm only going to round off my very final answer. So 60 pi units squared, because we don't know what unit it is. And then I'm going to work out my hemisphere, and I know that an open hemisphere, the surface area, is equal to half of 4 pi r squared. Where do I get this 4 pi r squared? This is, it's a half times 4 pi r squared. This is the area of a sphere, the surface area of a sphere, but I'm halving it because it's a hemisphere. And what do I know? That this cancels and it becomes a 2. So all I'm doing is substituting into 2 pi r squared. When I substitute in, 2 times pi times 6 squared, which is 36. 36 times 2 is 72 pi. And then I'm going to say units squared. So therefore, my total surface area of this ice cream cone, surface area total, is going to be 60 pi plus 72 pi, which equals 132 pi units squared. If you want to put that in your calculator and round it off, 152 pi is equal to 414,69. 414,69 units squared. And that, boys and girls, is the end of your examples. You're now going to do exercise 3 for homework. I hope you enjoyed this section as much as I did. I really enjoyed doing that experiment with you. I hope you enjoyed it too. See you, grade 10s.